chemical found in drinking water across the nation, PFAS.
The state is suing 17 companies that they believe are responsible for PFAS contamination.
Recent tests have revealed that dozens of cities across the U.S. have elevated levels of PFAS.
Hi, we are Team P3 Hawks from the Illinois Institute of Technology. We are a team of graduate and undergraduate students working under Dr. Lampert researching ways to manage PFAS contamination. Objectives for the project include conducting experiments analyzing the effectiveness of sediment caps on PFAS, developing methods for detecting PFAS using liquid chromatography and mass spectrometry, characterizing PFAS transport through the variety of caps using fate and transport models, and assessing the cost of the capping materials used. These are the types of PFAS we will be working with. In this project, we will be using a tank to simulate the mobilization and bioaccumulation of PFAS as it travels through sediment, and testing 3 different capping materials. The bottom layer will contain a layer of sediment contaminated with PFAS, followed by a thin layer of sorbent mixed with sand, and a top layer of water. The following clips show the sorbents that we will be using. In order to simulate the flow of a river, an aquarium pump has been purchased to circulate the water. In order to analyze the sediment, capping material, sand, and water, a peeper has been built. Here you can see that the peeper has a sampling chamber between 2 membranes. This is the membrane that we have chosen to use for our experiment. The first step of the experiment was locating sediment that was relatively clean and PFAS-free. Luckily, Norman Snitowski had offered up his backyard. The sediment was then transported back to IIT. Chicken wire fencing was tightly fastened by metal wires and zip ties to create a large sieve, which was used to grate soil into uniform pieces, as well as remove large rocks and roots. The membrane was placed in a sonicator bath to remove air bubbles on the surface of the membrane. The following shows clips of the peeper being assembled. The peeper was supposed to be assembled underwater because we wanted to be able to keep water within the sampling chambers. Water, sediment, and 3 types of PFAS were mixed together in preparation of filling the tank. We saturated the sediment until there was standing water. Peepers not being used were placed in tubs of deionized water to keep the sampling chambers from draining out. The tank you see being prepared here is our control tank. It's made so we can see how PFAS would regularly behave in our sediment. In our non-controlled tank, our sorbents and sands will have a mixture of the numbers you see on the screen. What you see here is the peeper being pulled out of our control tank. In order to retrieve our sample from the peeper, a needled syringe is used to puncture either side of the membrane to access the sampling chamber. The extracted liquid is then placed in a container to be shipped off and analyzed. The samples will be analyzed using liquid chromatography and mass spectrometry to measure the amount of PFAS in each sample. Liquid chromatography separates the PFAS from everything in the water and each other, whereas mass spectrometry measures the amount of each component within the solution. We're going to be using the CapSim model, a fate and transport model for pollutants and sediment caps. We will use CapSim to interpolate our experimental results. This is a simulation showing PFOA through the granulated activated carbon-amended cap. As you can see, the concentration of PFOA in the sediment decreases as it moves up and is adsorbed upwards. We are going to use the model in our design to assess the effectiveness of materials to find the optimal design for a real contaminated site. In Phase 2, we would like to look at more PFAS compounds, about 25 to 30, pore water upwelling and bioturbation, and implementation of this design at an actual site.